Finding the derivative function. Our objectives are to define the derivative function and identify where a function has no derivative. Recall that derivative means slope of the tangent line. That's also the instantaneous rate of change. So when we found the slope of the tangent line, we started by looking at the slope of the secant line. Let's just do a quick recap of what we did. So ultimately, we're looking for the slope of the tangent line at this point P, that point of tangency to this blue function y equals f of x. I'm going to assign that P value to have the x value c. And then the other point on the secant line to have the x value x. And therefore, the y value on the function f of x is corresponding to f of c and f of x. And then when we remember what is the slope of the secant line, we recall that slope is change in y over change in x. So of course that means we're doing the change between f of x and f of c over the change between x and c. And then because we want the slope of the tangent line, we are bringing x closer to c. So when we get the slope of the tangent line, that includes the limit as x approaches c of that average rate of change, and therefore altogether makes the slope of the tangent line, or the instantaneous rate of change, better known as the derivative. And we called this f prime of c, the derivative at a point. F prime of c equals the limit as x approaches c of f of x minus f of c over x minus c. Now another way that we could describe this is saying that there's a difference between these 2 points, this distance in x, as being h units away from each other. So we can still call this f of c because I'm still going to call this x value c, but now instead I'm going to call this x value right here c plus h, the distance between those x values. So this y value up here becomes f of c plus h, and then our change in y becomes f of c plus h minus f of c, and our change in x is of course already defined as h. And if we are trying to find the slope of the tangent line, we're bringing this c plus h closer to this c, which means that we're making the change in x, or calling it h, get closer to 0. So this is another way to define the derivative at a point. The limit as h goes to 0, that change in x goes to 0, of the difference in the y values over h, which is the difference in the x values. Recall this is our difference quotient. So when we take the limit as h goes to 0 of our difference quotient, that's another way to find the derivative at a point. The derivative function can be written quite similarly to that. So f prime of c means the derivative at a point. F prime of x means the derivative at all of the x values on the function. So notice how we replace the c being one x value with x being all the x values. And to find the derivative function, we're using the limit of the difference quotient. Please note that it is known that if f has a derivative, then f is said to be differentiable. Again, that's when f has a derivative, possibly a new vocabulary term for you. Let's take a look at this example. 1. Differentiate the function f of x equals square root of x plus 2 and determine the domain of f prime. So remember that differentiate means find the derivative. And because it's not asking for the derivative at a point, we want the derivative function. So let's use the fact that f prime of x equals the limit as h goes to 0 of the difference quotient f of x plus h minus f of x all over h. And let's apply this to our function. This will be the limit as h goes to 0. F of x plus h means where the x is in our function, we're plugging in x plus h. So that becomes the square root of x plus h instead of x, and then plus 2, minus f of x just how it is, which is square root of x plus 2, and then all divided by h. Now, of course, when we evaluate a limit, we try first substitution, plugging the 0 in where the h is. It yields 0 in the denominator, so that's not going to work here. So what can we do? Well, we know that when we have a radical expression, often rationalizing will work. So I'm going to multiply the numerator by the conjugate of this expression, which is square root of x plus h plus 2 plus square root of x plus 2. And then, of course, we also multiply the denominator by square root of x plus h plus 2 plus square root of x plus 2. Let's see how this works. Limit as h goes to 0. When I distribute this, that leaves us without the radical, x plus h plus 2. Multiplying the outers and the inners are opposites and make 0. And then negative square root of x plus 2 and positive square root of x plus 2 is negative of the expression x plus 2. Divided by, of course, we have h, and I still have this expression that I'm going to write multiplied to h. And let's see what this does for us. We've got x minus x, 2 minus 2, and I'm left with just the h in the numerator. Let's follow through with that. Limit h goes to 0, h divided by h times the quantity x plus h plus 2 plus square root x plus 2. And notice h divided by h leaves 1. And now I should be able to use my direct substitution again. So h goes to 0, plug the 0 in for only that little h right there, and let's see what we come up with. 1 over square root of x plus 2 plus square root of x plus 2 is a valid answer, but we can clean that up a bit. 1 over 2 square roots of x plus 2. And this is our derivative function, f prime of x. Done. Now the second part of this question says, determine the domain of f prime. Let's begin by checking out the domain of the original function. Now, of course, a radical function can only be positive. We can't take the square root of any negative values. So we're going to start by saying that the stuff under the radical, x plus 2, can only be greater than or equal to 0, which means x can only be greater than or equal to negative 2. Now our derivative has square root of x plus 2 in the denominator, and the denominator can't equal 0. So not only does this have to be true, but x plus 2 can't equal 0, so x can't equal negative 2. So therefore, the domain, when we combine these, leaves us with x such that x can be only greater than negative 2. Number 2, determine whether the function f of x equals 3 minus 4x if x is less than negative 1, and 2x plus 9 if x is greater than or equal to negative 1, has a derivative at c equals negative 1. Now notice this is different than the one where we wanted the derivative function. This will be the derivative at a point. So when we see that, it's often more useful to use f prime of c equals the limit as x approaches c of f of x minus f of c over x minus c. So we want f prime of -1, the derivative at c equals -1, which will be the limit as x approaches -1 of f of x minus f of -1 over x minus -1. Now notice this piecewise function is possibly split apart at -1, or at least we use this expression when x is less than -1 and this expression when x is greater than or equal to -1. So we're going to have to find this limit by doing the one-sided limits first. Let's begin with the limit as x approaches -1 from the left. Well, from the left is which one of these? That's right, x is less than -1. The left side of -1 is to the left. Greater than is to the right of -1. So starting from the left, we're using that top expression, 3 minus 4x for f of x, minus f of -1 means I'm plugging -1 in where the x goes. So 3 minus 4 times -1. And that's divided by x minus -1. Now, what can we simplify here? 3 minus 3, and the numerator is left with -4x minus +4. Let's rewrite our limit expression. Limit x goes to -1 from the left of -4x minus 4 over, and of course that can be simplified to x plus 1. I notice I can factor here, so this becomes the limit as x approaches -1 from the left. Take out the -4, and we're left with x plus 1 over x plus 1. The common factor divides out, and our limit from the left is -4. That was the first side. Let's do the second. From the right, we're using that expression. Limit as x approaches -1 from the right. This time our f of x is 2x plus 9 minus our f of -1 means we're plugging -1 into 2x plus 9 over x minus -1. Let's see how we can clean this up. We've got 9 minus 9. That's gone. Limit as x approaches -1 from the right. 2x minus -2, or 2x plus 2 over x plus 1. And I think you see it. We can factor out the common factor of 2. And x plus 1 is gone, and that limit is +2. Now what does that mean? Notice the limit from the left was -4. The limit from the right was +2. Those limits do not equal each other. So that means that limit right there does not exist. And since that limit represents our derivative of f of x at -1, then therefore f prime of -1 does not exist. Thanks for watching.